For our research seminar today, it's my great pleasure to introduce Dr. Sathya Ravi, who is an assistant professor at the Department of Computer Science at University of Illinois, Chicago. Dr. Ravi holds a bachelor's degree in computer science from National Institute of Technology, Trichy, India, and MS in Industrial and Systems Engineering, MA in Mathematics, and PhD in Computer Science, all from the University of Wisconsin, Madison. Dr. Ravi spent summer of 2018 at Amazon, where he worked with the recognition team on various computer vision problems on semi-supervised settings. Dr. Ravi's primary research interests include deep learning, parsimonious algorithms, and computer vision. More specifically, he is interested in numerical optimization of deep learning systems and in using deep learning to solve vision problems efficiently. Some of the tools that his lab has developed includes DeepCG, fast flow filter, visual tensor decomposition, just to name a few. I'm excited to have Ravi speak at our colloquium today. The title of his talk is how to change the title here. So how to use SDEs for deep network-based predictive analysis without a single SDE run. Thank you so much for being here, and take it away.
Thanks, Vidhu. Thanks for the nice introduction. I'm very happy to be here. Could have been warmer, but I think it's fine here. Yes, I did change the doc, and if you saw my abstract, I also changed the ordering of the parts. So when I was making the final changes last night, I thought that maybe I put the card in front of the course. Doc, it's going to be nice, better than what so first, I will talk about just give you a little bit about my background. Currently, I'm in the CS department at the University of Chicago, a few blocks south and west, where I lead a vision plus machine learning lab. So today I will talk about some of the work that I've done in the last couple of years since I've joined here. Before that, I was a PhD student in Madison. Finished my computer science. And even before that, I was in India, in the southern part of India. So, so my background is kind of spread out a little bit, with my research interest revolve around computational and numerical aspects of deep learning. So I'll give you a primer if you're not used or know what deep learning is. Talk. Mostly I've done, as Stu was saying, visual setting, and now I'm also trying to work with students here who are interested in natural language processing, which involves parsing text data. So I have two main directions. The talk is also one direction, two parts of the talk. So I worked on, I've been focusing on fairness aspects of machine learning models, what that means is instead of just focusing on the average accuracy of the data set, we want to also obtain good levels of accuracy in the subgroups. So that's one theme, one set of problems. There's also this fine-tuning aspect, which is now a really big deal. Big models that Google, Microsoft kind of puts out every few months, and then how do those models actually, what do those models mean for my problem I want to focus on? That's at a high level, we call that as fine-tuning. And the other one is interpretability, which is basically trying to understand. So these are all really related in some sense. Interpretability is basically trying to understand which parts of the model is responsible for predictions. So we have a CEPR paper coming out in a couple of months talks about unlearning of models. So for that, we do want this to be, we use this as a guiding principle. And also feel free to interrupt me questions. Few tells me it's supposed to be light talks. So
it's an informal group, so if you have any questions, please feel free to.
I don't have any big message. It's a lot of themes. The second one that that you'll see once I begin my main work is about talking about dynamics of the features and the input data as you pass it through a network. You have an image, you have it as an input image, but once you pass it through the first few layers, now it's just numbers. It's not image anymore. So this graph neural network has been said that if you can exploit the spatial structure available in the input data, and while you're propagating input, then apparently it's been said as a really nice thing to do, because you're not treating each prediction as an individual function, but rather it's a collection of the function to find out the whole data set in some sense. So what I've been doing was, as you can see from my talk, trying to find connections between these graph neural networks and some of these more classical objects that we call differential bridges. I'll show you very good examples at the beginning of the talk, so to convince you that differential equations are actually pretty fun to study. So to get the main what is deep networks? That's always a question. So I want to get that out of the way. In this talk, whenever I say deep network, I just mean you have inputs that are you stack on the left-hand side of the monitor in your early stages of your input pipeline. That's left-hand side. And then, now everything has to be nodes and edges. So what we do is initialize the input data you have as the input nodes of a neural network. And then now this input data is going to get processed a few times. And that is indicated by these edges. You can think that if you have data first coordinate 1, this 1 is going to be transmitted all over the edges. It goes. So on top of these edges, we have some weights, which gets multiplied by the input to that edge. We have lots and lots of them. So more recent constructions, recent models that people use, you can have this L, which is called the number of layers, to be even up to 100 or 200. So there are neural networks that have enormous number of weights that need to be trained in some sense. And then finally, at the last layer, we get the output of the neural network. So what does this have to do? So if we consider that as a deep neural network, what does it have to do with differential equations? There was a 2019, I think, paper, Europe's Test of Time, Best Paper Award, top conference in machine learning, which said that you can actually look at a neural network as an ODE. So I haven't yet explained what it is, but for the most part of this talk, this will be the definition. So your features, so Z represents the features. So Z here represents the features, and L+1 represents the features at layers +1, and you can see that it is a function f sub L, which means a function at lth layer applied to the features at C of features. Okay, and what they found out was that if you use so this residual network was the most common neural network that if you Google best differential classification models, you will get to see that residual networks is one of the top networks. I use them all the time as well for my papers. What they basically said was, if you think of the residual network, which exactly does this, then an ODE network is just a smoother form of the same residual network. So as the features of what you're seeing in the plot is the same input, same set of inputs. So you have 1, 2, 3, 4, 5, 6, 7 inputs, and they get propagated as you go to the page. So input that was -5 is now slightly less than 5 in page 1, slightly less than 5, greater than 5, -5. It's either all greater than -5. But then you will see that there represents a path of the input features as they move across the layers. And one thing that optimizers like me like is having things that are smooth, because if things are smooth, then we know where they're going. And that was the main contribution of this. And what they basically said was, you write the first equation, at least formally, as z is getting changed. So here the main connection is to note that t and L are somehow related to each other. So t minus t, if you look at the French equation, you see zt minus 1 to be equal to that goes on the right hand side. So where are neural networks? So these are the neural networks that you train. Theta are the parameters. F is whatever you choose, activation function, and so on. And then you set up the loss function. So this loss function is the you can see that how the way it's calculated is you take your input data and then solve the ODE or time, give it to the ODE solver, and then you'll see what the iterate is time, and then you have to compute the loss function. So this is all known. And the way we train the parameters is by changes. So that are those are the preliminary. So these are this is the work submitted to ICML this month, and I hope it gets accepted. So Harsh has been a main powerhouse in making this work that I'm going to present, and experiments. And Mohan also used to working with. So here are some differential equation examples. Very sure, like me, when I started looking at CS differential equation, I didn't see much. So I did. So there are two types of equations. fields of mathematics. Linear equation, here we mean linear differential equation. What I'm showing you here is a path of one particle. Coordinate 1 is start at 1, 0 coordinate, and then you run the differential equation. You see that it just goes along. It traverses the path of a circle, some center at the origin. Why is this linear? It's linear because if you have two, there are nice properties that you can exploit in the sense that pixels have the same angle in on the x-axis, then you can know the trajectory of red given the shrinking. So in a solution transform, you transform one solution to the other pretty easily, and these are called linear equations. And this is, I'll show you soon an example called why this is important equation. So now the question is, why are not, if this is a linear equation, can you show me a nonlinear equation? Yes, I do have one. So this is what we call as Lotka-Volterra differential equations. This is used in fishing industry. Lotka was a fishing. One of them was Sweden, and they're working on looking at how the population of fishes change depending on how we keep the pond or lake. And they saw that initially what you're seeing here is in their example, the coordinate 1 is really think of this as the fish, and then the coordinate 2 to be the food level consumption. So fish will have, if there's no food, then fish won't survive. If there's no fish, then the water is going to go back. So initially you set that provision, and you can see that if you set the food population and the number of fishes to be that much, then over time, you see that equilibrium solution goes to something else. It's not zero. So this is a valid nonlinear equation. But why is it nonlinear? Well, you can see that if you have 2 points that are kind of close to each other, then they go to the same fixed point, converging to the same point. In the case of the circle, the fixed point was just the origin, to remain the same for the whole thing. So here you can see that again, the fixed point remains the same, but the motion is very different. You take points that are farther apart, and you see that at various times they meet and their trajectories are close, but they're really not close to each other. But eventually they're going to converge to the fixed point. And really the reason why differential equation, I call this a nonlinear, is because if you, because of the last plot, this is the same simulation, but just changing the parameters, define the differential equation slightly different, perturbing the parameters. And you can see that the results are different. In a linear equations, if you change the speed of how fast you're traversing the circle, you're still going to traverse the circle. Okay, so these are the examples, and there's been applications and vision. These are already implemented. I'll tell you why we need to still know differential equations in a second. But anisotropic diffusion and anisotropic filtering are two very industrial scale applications. You can do it in 40 frames per second sometimes. And they work because they have a really nice closed form solution. Same with in image processing, we have rotations of images. Here I'm showing you a kind of generalized form of rotation that you can model. So, so what is now? I talked a little bit about differential equations. What are stochastic differential equations? So we are going to just take very simple definition. Years worth of study on that. But really, I mean, so if a differential, we add a certain term, this is stochastic. So otherwise, what you saw, equations remains the same. At least formally, we add a stochastic term to the differential equation, and we call this as a forward. Show why we call this forward is the, and so when you see this, the next question is, well, how do I run the equation? Do I have a similar representation for, like we have the normal differential equations? And the answer is yes. Here is it's similar. So here this so the t is the current iterate, current position of the coordinates. Xt plus 1 is the new iterate, and this will be your step size. You have to choose, right, because it's a discrete algorithm or iterative algorithm. The only thing that you have to make sure is to convert this dw into a Brownian motion. To draw a random sample from and then there's also a factor of square root of t. So we use step size of delta t for, think of this as rotation, rotating pixel or the particle by delta t amount. And then you're adding a little bit of noise to it. So that little bit of noise that comes from this normal distribution, that's the real, that's the difference between deterministic differential equation and stochastic differential equation. And so when you add this term, every time you can see that if you run it twice, you're going to have different results. Okay, so so where are these used? So the anisotropic filtering and the fusion that I showed, those are just input-output mapping because it's deterministic solution, deterministic differential equation. But for SDE, you can have more interactive applications, showing you common filter denoising on the left. That's denoising scans. So this is a big scan. But I worked on MRI. But those pipelines, whenever you take a scan of your brain, scan, the denoising is at this point, I think most of the scanners have them by default. So most of the technicians, they first have to calibrate them. And it also, as you can see, it depends on, this is a simulation, so you're adding random noise, but in a real-time setting with patient movements and other things, we're going to have to capture that. So the other one on the right is common filter tracking. The main thing that you have noticed is at this point, you can see that the plane was blocked out by, sorry, let me just say, yeah, that is a plane. Plane, when it was occluded by clouds, you can see that the common filter is still able to follow the deterministic path, so it catches the plane. type of issues. So yeah, so we have a drift term and a deterministic term. Drift term F in the stochastic equation is usually is thought of as a deterministic portion that you have to perform the models. In this case, you might say that an object is going at some velocity. Then you have to perform F, and the noise will depend on what kind of is it being good? Is it going to rough? Is it going to windy environment? Because then it's going to have noise, weather, things. Okay, so I think this might be easier. So what we did in this work is use these SDEs to develop newer generative models. So I'll tell you, generative models mean that you have some images that you take as the input data, and then the goal is to find a neural network, showed you before, that can generate these images. So if you have a photo neighborhood of good things, if you have a photo of animals that you see, or bunnies, or birds that you see in the park, then you might want to see, you might want to train a neural network that can do some of the capabilities. Yes. So once you train them, you don't need the training data, you use the samples that the neural network generates. So what we consider in this work is, if you're given a stochastic differential equation, you need neural networks to follow its trajectories. Or in other words, if you know a way, there's a way that images get corrupted, or if it gets changed over the course of time, then can we inform the neural network about properties of F and G. These are completely different so far, and that's the question considered. So it turns out that someone else has already thought about this exact same problem in recent times. And they said that it's possible to do so with what they call as time-dependent neural network approaches. So why do we need time models? So there was a famous result, this is in the 1970s. It said that if there's a forward way to run stochastic differential equations, I just showed you a few slides ago, then you can reverse the process by this particular stochastic differential. We call this as inverse SDE. As you can see, these terms same as before. This is different. And what I mean, the idea is to kill the drift terms. So that's the idea. To formalize that, you need this notion called as score function, which is nothing but input data at the time t, and have the gradient of that. So the idea, I mean, again, when you find such a mathematical result that says you can do something until now wasn't possible, then the idea that some of the recent work proposed is to, well, what do we, can we just learn the score function using a neural network? So this is okay. So if we know the score function, then we can train a neural network so that at each time point, we know what drift function to kill off, and then use that stochastic. Okay, so what is, so now I think I've just discussed some math, how to set up the loss function. This is a lambda t is just a positive weighting function. Don't worry about that for now. The second expectation, x0 is your training data, right? So 0 is training data. It's here. And then finally, we have this innermost expectation, which, as you can see, the expectation is over x sub t, which means that we have to iterate, solve the SDE to compute the iteration at time point t, and then compute the loss function that here. So this was great, and they also, in fact, proposed exactly what we saw in the last slide: take the difference and square them. So with a loss function, this will be xt is the image of t. 0t is the density at initial, that's a typo. X0 is the initial, original image. P0t is the density at positive 8. Let's take it. So where we started with is many of the work that we saw until we started working on this was that they only talked about F to be very trivial. What it means is that F has a closed form solution, so they don't need to use complex data processing techniques or data augmentation techniques. Here, so we extended to some what we call it as a simulatable F processes. That is already there. So, for example, showing a practical example, pixels. So there's the first row. What I'm showing you is the image of a cat that is rotated by a certain angle about the center. So the center would be here, and as you can see, the center remains the same. So it's rotating about the center. Clockwise direction. So this you can do with scikit. You don't need EM. You have a SciPy or NumPy or OpenCV2. It's a one-line code to rotate your favorite image. But the second one, you'll see that you actually have a cat in your home, which I do. This is not a cat. You can do other things. So this Ladka Terra, this is the one that I showed you a few slides ago. You can see that it's kind of trying to squish the, so just rotating them in a very rigid fashion. So this is rotation rigid. But we are still doing, so the second row took a lot of effort. Harsh had to spend a night or so to get the numbers right, because the trajectories could be very of these pixels. What we essentially have to do is, put the image of the cat in bigger canvas and then rotate to see where the new coordinates are, and then values on the whole. But it's very easy to do it when you're just rotating, because you have all kinds of niceness that's coming along. Whereas if you want to squish the face, stretch it, then have to actually do the rotation. There's also the extreme one. On-off camera, see that, which basically rearranges the whole entirety of the pixels CAD, and it's periodic. So you keep doing the same rearrangement. I think this CAD has, if you do this 100 or 150 times, you will get back the same. So this is periodic, which is very surprising. So we added, so to do that, you have to just write 2 or 3 more lines of code here than what you do if you just rotate. If you just want to rotate, you have to cycle library or so coming back, how do we inform the generator? So we want the generators or deep networks to produce images that I showed you before, but there's still a challenge, as I was just pointing out, there are lots of limitations, lots of reasons to solve differential equations. So, well, if the iterates depends, the chicken and egg problem. So what we said was, let's say we have only one out of the whole trajectory of the neural networks. Let's say we have one time point, so rotation sense. You might think, let me collect all images and then rotate them 30 degrees. So that's a similar situation here. So we run the for SDE to get the so if you do that naively, you have 2 iterates, so you can train one for the first iterate and then other model for the intermediate iterate. That would be okay. But what we propose is use a different regularization function, wherein we said change an encoder for that iterate. So this regularization depends on toe, which I call this needed. So you can see we have a encoder. S data is the smaller portion of the bigger model. Showed you, I just talked about, and then we have its own decoder as well. So basically, instead of having 2 different models, what we have is you can have one big model and then use portions of the model for training, for using this extra substance. And you add it to the loss function as on top of what they do. And to implement this, there's a nice, actually a reviewer pointed out that we should draw our figure in fifths. So exactly with that. So, so we have a neural, so this is the generated model. And here on the left, I'm showing you iterating the images from given data at 0 to some. So the main part that you have to notice is that as you keep iterating, because it's a stochastic differential equation, at some point you're just going to see noise. It will be completely noise. And so what we do is, so we use the fact that there's a nice relationship between how far you run the trajectory and how far you have to move the network in order to find images of the same quality. So for example, say this is a high quality image. This is a low quality image. And so, of course, a high quality image has a lot more information about what we want to generate. And so it directly goes, so the high quality images, they don't need to get processed, they don't need to get encoded by a whole lot. And so they go directly into the encoding of the space and substance. Whereas the high noise data that we use, they have to get processed by the whole network. So they have network, whereas the high quality data used to train the random space and substance. So when you do this and train all, so these are all E's and D's, so parameters that you can train, and I'm going to see that images that you get are worse than what you get if you just use the training data and substance. And there's a, I mean, so this is what we do in some sense is construct a coupling between the stochastic differential equation and generative sort of like I like to imagine like a Velcro stick in some sense. So what we're seeing here is you have to stick of stochastic equation in the slope-based layers generative model. So I'll just quickly some results. So yeah, we saw point cloud denoising is supposed to be a nice, it's a hard task because what you have here is, see this. So these are noisy points of leading point cal. And the goal is to get the denoised version. Here, what we do is in your training data, you always have the noisy and the denoisy point clouds. So you can create a lesser noisier version by just taking the average of the noisy point cloud and the clean point cloud. That gives you a less noisier version. That's what we use as the intermediate iterates here. Additional layers added to. So what we do is we use this multi-layer perceptron as a predictor, and we use a slightly more dedicated predictor for the intermediate iterates. So we were also able to show that we are actually finding more decoders and encoders that have a plot here. Shows the distance between the encoders and decoders. As we keep training, they kind of increase, showing that you are actually getting two different encoders. So that was the first part. Quickly, the second one. So the second one I want to discuss is about modeling instantaneous flow of features. So here the flow is what we, so these features. So what we want is we want to see, we want to model how features of a neural network as an output, how do they change as you get more and more data? That's the question we want to hear. So instantaneous just means that you're only calculating it at this time point. Later means that so all this started from looking at this one vision like types. This is the gradient descent vision. So what we have is here, I changed the notation a little bit because this one is a published paper. So this is our ICCB paper, and Xiang has some slides as well, video as well. So I'll go a little bit faster on this. Here, W is the parameters, and you have some loss. So I will choose loss function as R. Writing this, I was thinking that this has risk. So it's the risk function. So choose R. And Z is a random variable here. And T is some transformation that changes the data. So takes data and rotates or crops it. Okay, so instead of if you now kind of parameterize that T as a sequence of transformation that can be captured by this stochastic equation, then what you get is data augmentation. So this captures the notion of augmenting data by changing data a little bit, and it also captures updating parameters, which are using that data TZ to compute the gradient, update parameters. Same stochastic differential equation, FMG. I had FMG before, now it's sigma, otherwise same. So and then we have vanilla DNN. What we want to do is, if I want to represent it in a graphical form, this X, which is the layer input, it gets transformed by this forward Z to XT, and then that will go into a network for training. So that's what we call as deep neural network stochastic. So that's what we want to model. But the problem really is, as I showed you last time, each XT, when it's a stochastic differential equations, they have different trajectories. See here, each X might start at the same point, but because of the noise, you might end up at completely different final positions. And it can be very expensive to iterate or do this at every iteration. So what is what can be the solution if you're interested in f of x and t? So the idea is to, again, draw a space of x. So now as a machine learning, well, yes, each x is going to go wherever it wants to go because it's getting stochastically transformed. But if I know the whole space of x, and if I have enough samples of x, well, I will know how to compute xt in a much easier fashion. So that's kind of the idea here. We'll see, and that's possible to do this particular reasoning. We need to know this concept called as infinitesimal generator. So these generators are, this infinitesimal generator is defined for a function. So it doesn't take a coordinate, it takes a function. So it really takes a neural network as an input. And what you have on the right is the usual calculus derivative definition, although there's an expectation in x of t. So this is it is instantaneous also, because this limit should always indicate to you this whatever you're computing is an instantaneous quantity. So what we claimed was that this L can get us the desired trajectory of x without extra sampling. So in other words, what this L, I don't know if you've heard of the Laplacian before, which is big because of diffusion. What it said was if you compress the whole space to Gaussian, here you're compressing this whole stochastic space into this infinitesimal generator, and this was some people harmonic analysis reference here. They came up with this idea. And what they said was, if you have samples from X, a bunch of them, then you can compute a matrix L from M, which can be an approximation of L, as long as the number of samples, if you have enough samples. So we proposed, so they told us how to calculate an approximation of this infinitesimal generator. So we tried this. What we wanted to do was just plug in F to be a neural network into this definition. And what is it going to be useful for? You have to unwrapped limit definition and you rearrange the terms. And then you'll see that what you're actually computing is an expectation of the function value in the near future as prescribed by all samples expectation. So FW at a slightly future value is given by the neural network output for its own sample. And then you correct its prediction by these by this matrix. So what does that look? So instead of actually running this differential equation and then putting it to the network, what we do is take a bunch of samples, estimate L, take the samples to F directly, and then adjust it. We have the algorithm here. It's GPU kernel density estimation. Simple, and showed how even for Resnet, you can kind of have what I call as post some kind of mysterious accuracy boost. We still don't know why it's because the model is trained, or even if you have your model trained out, you can still use this PMD layer construction. See that just the inference with the same weights, the inference can go up by 10%. Pretty surprising. Fairly standard data set. Skip. Yeah, we also have this, we did the same thing with point cloud prediction. So there we're doing point cloud denoising. This is the point cloud prediction, much easier to understand. We have a point cloud representation of an object, and we'd like to classify what object represents. We believe these would be useful in personalization things where you can describe objects by small number of points. Just want the user to kind of associate those points to an object. So here, as you can see, this is considered the model. What we do is we place this network. They have lots of layers. We took down a bunch of layers and then replaced it with this Gaussian. And here as well, we get pretty close to the state of the art just by these are results from last year. So it's not that new. Top here, future dimension. So I'm mostly as I was trying to, I got trained as a convex optimization person. So now I'm doing other non-convex, solving, these days I solve non-convex problems, but essentially there are lots and lots of problems at the intersection of non-convex and convex problems that not been explored that much, especially for small scale data sets. That's something I'm interested in. And the other part is SDEs, and the SDEs seem like a topic that keep on doing more and more interesting problems. So I'm trying to use design new layers of networks to solve convex problems, even non-convex ways. We're also investigating some applications.
Right. Questions?